Essentially, I want to tell you about nonconvex optimization. And I will, essentially, we talk about methods here based on the fact whether they use derivatives or they don't use derivatives for the problem. And whether we have constraints, restrictions on the variables, or we have no restrictions on the variables. And then I want to talk a little bit about the case when we don't have derivatives, and then to go into even more approximate situations where we do most things inexactly or probabilistically. There will be another advanced class on optimization in the second term, probably on discrete optimization. But I also want to see, if you have special needs or interests that you would like us to discuss, I'm quite flexible to make that second part more whatever suits your interests. Okay, so my research is in optimization and non-convex optimization, and at the end I will say a little bit about my research connected to what we'll talk about today. But mainly I just want to give you a survey of what are the methods that we use and what can they do for you. So we are talking very generically about minimizing a function, okay, subject to being in some set omega. So f is a function from Rn to R, and for the beginning and essentially throughout, I am assuming this is a smooth function. Okay. And this set omega, I'm assuming that I can write it down as coming from finitely many constraints. So for example, my variables have to be in a box, okay, for example. Or my set, in a box in the sense that, for example, x cannot exceed some value or cannot be, say, arbitrarily close to 0 or negative. Okay, so a lot of these restrictions on the variable comes from physical constraints, restrictions. The other issue that we are concerned with in general is that we want these methods to be scalable. So in particular, n may be very large. Okay. Now I'm saying that we are minimizing because without loss of generality, I can transform any maximization problem into a minimization problem by dealing with minus f instead of f. Okay. So that's why without loss of generality, I can say we are minimizing. Right. So what do we mean by a solution? Okay. So really, I'm going to go through the fundamentals of optimization here, of continuous optimization. Okay. Hands up, who has done optimization before? Okay, we are doing well this year, I have to say. All right, then I'll speed it up here. Okay. But you slow me down, okay, if I go too fast. Right. So we could have global minimizers or local minimizers. Global, we say a point is a global minimizer if f takes its smallest value at x star. And we have a local minimizer if around the point x star there is some neighborhood, there is some area, there is a ball or a box such that if I intersect that ball with my feasible set, I see that f takes its smallest value at x star. So if I'm sufficiently close to x star. So here's a 1D example. I minimize f of x in an interval ab. I have this oscillatory function. And what we have is that, for example, in ab, right, we can say that this is the global minimizer. And these are local. This is a local minimizer, right? I can find an area here that where f takes its smallest value if I look at feasible points and that interval around x2. Okay, have I missed any point in AB? I have missed one. X equals A. Okay, the boundary point. If I look at x equals A, and I look at an interval centered around A, okay, and I intersect that with my feasible region, I can see that f does take its smallest value at A, if I'm sufficiently close to A and feasible. So those type of points are special points called constrained minimizers, and we'll talk about them in the second part of the talk. But first, I want to talk about unconstrained optimization, where I have no restrictions on the variables. And so all these points, x1, like x2, and so on, or even points like here, okay? So outside of any interval, any feasible domain. And furthermore, we are going to go to things that are quite nonlinear and in higher dimensions, right? This non-convex landscape can look pretty crazy. For example, here's one of the standard examples in non-convex optimization, the Rosenbrock function, which has only one stationary point, is bounded below, has only one stationary point, only 1, 0 of the gradient, but it's actually non-convex and provably non-convex. And you can see here, and also it has this valley, this banana-shaped valley. And it is actually quite difficult to optimize it accurately. You encounter ill conditioning as you approach this and try to enter in that valley. Okay, right. So in optimization, we talk very much about classes of problems. What I've said until now is very generic, and things will remain quite generic because we are trying to develop methods for large classes of problems. So, but on the other hand, if you know something about your problem, you should probably use a more specialized algorithm. So there are some standard structures like linear and quadratic problems, which are also the simplest forms of the more general problem. So linear programming are optimization problems where you minimize a linear objective subject to finitely many linear equality and inequality constraints. You also have quadratic programming where you have C transpose X plus this function here, this quadratic function in X, again subject to linear constraints. So here C and H are given, and the AIs and the BIs are given problem data. If H is convex, okay, if H is a positive semi-definite matrix, I will get back to that later. We'll see in a moment the shapes of this quadratic problem. Actually, let's postpone for now. So these are the simplest forms because if you look at the linear case, your problem data depends linearly on the variables. So the gradient is always constant, this vector C. And for the quadratic problem, you have a linear gradient and a constant second derivatives. All right, so these are quite simple, linear and quadratic dependencies on the variables. These are quite the simplest thing we can think of in a continuous world. And the more general class that we will talk about today is this constrained or unconstrained, where we minimize a generic function, possibly using derivatives. And then we have these nonlinear equalities and inequalities, possibly non-convex. Okay. Now, if somebody gives you, this simpler problem, if your problem is simple like this, you should not use the methods we are talking about today. You should use more specialized methods. Okay. But if your problem is not as simple as this, then you may want to consider variants of what I will talk about in a moment. All right. Now, the problem is that I can't yet start talking about algorithms, especially about derivative-based algorithms, because I don't know how the definition I gave you for minimizers relates to actually me being able to design an algorithm for this problem. So can I characterize my solutions in terms of derivatives? That's the first question I'm going to ask. Can I have an algebraic characterization? Can I have a relation to derivatives or some other kind of algebraic characterization that allows me to use that in an algorithm design? If I have derivatives. So for the first part, assume that we have at least first derivatives. Okay. So what did we notice in this, right? So if I look at what is the derivative of a, how can I see the first derivative of a function?
Slope.
The slope, that's right. So what happens at minimizers? The slope is 0, right? Okay, so indeed, this is from year 1 calculus. So we have that at the local minimizer, the gradient, okay, so we have a continuously differentiable function, a smooth function, don't worry about C1, okay, really. And then if we have a local minimizer, then its gradient is 0. And we call any such point with 0 gradient a stationary point of f. Right. So let me try to give you an insight as to where is this characterization coming from. Here's a fact. And it's good for you to remember this throughout this presentation. I have a function that's smooth. Okay. I have a point in Rn, and I have a direction that's non-zero. Then, if I have this property here, if the gradient of f at my point x transpose s is negative, this transposition is just inner product. Okay? Who doesn't know what transposition is? Right, so I'm just taking the sum of the products by components. If this is negative, then I can ensure that my function goes down from x along s for sufficiently small and positive alpha. So in other words, s is a downhill direction. So if this property is satisfied, then I have this. Okay? This property is always satisfied by the negative gradient direction, provided the gradient at the point is not 0. This you may have encountered in other contexts. So if I have a point, the negative gradient is always a downhill direction. Right? So if, provided it's not 0, right? If I'm at a minimizer, I shouldn't have downhill directions from that point, because it can't be a minimizer, even a local one. Okay? And so it must be that the gradient is 0. Okay, so let's think a little bit more about this. So let's think of the negative gradient direction as a very insightful direction. Okay? I can move along it and decrease my function for a sufficiently small alpha, not for any alpha. Okay? If I stay sufficiently close to my base point x. All right. Now, what this property is telling me is that any direction that's not too far from my negative direction, negative gradient direction, will also be descent for my function. So let's look here at this very schematic drawing. So here I have some contours of my function. I plot my contours in a 2D plane. The minimizer is somewhere here. The negative gradient is pointing to that minimizer. Okay. And the negative gradient is pointing to that minimizer. And any direction pk that forms an acute angle, an angle less than 90 degrees with this, will also point in similar direction. If the negative gradient this direction pk is orthogonal to the negative gradient, so it's somewhere here, then you can see that it would keep me on the same level set of f, and I wouldn't be able to go down. Okay? And if it's an obtuse angle, it would take me uphill. Okay? So I think of the negative gradient direction as sort of a reference direction. And then everything that's not too far from it is fine. And indeed, why am I saying this? Because this condition here, you can write it in terms of the angle using the cosine formula for the angle between two vectors. And you can see that this angle, if this is true here, if grad f transpose s is negative, then the cosine is positive, and so this angle is less than 90 degrees. All right. So we've learned something. The negative gradient always downhill, and 0 if I'm at a minimizer, or any direction that's not too far from the negative gradient will also take me downhill. Right. Okay, so now we'll pause for a moment. This almost takes us to methods, but I'm not there yet because I want to first finish with optimality conditions. So we said that at a minimizer, the gradient is 0. But that's not enough, right? There are points with 0 gradient that are not minimizers. In particular, any maximizer also had 0 gradient. So to be able to distinguish between minimizers and maximizers and saddle points, I need to look at curvature. So I need to look at how curved my landscape is. So in particular, right, what do I notice here? Okay, around minimizers, I have a shape called convexity. And along maximizers, I have concavity. Okay? So I want you to, those of you that do not know convexity is just essentially this kind of shape, like a glass that holds water, or an concavity, which is like an upside down glass. Takes a long time to describe convexity otherwise. I will describe it in a moment in terms of second derivatives, but it's not necessarily easier if you've never seen it. So this kind of curvature will give me a minimizer, and this kind of curvature will give me a maximizer. And if it's in between, it will be a saddle. We'll see a bit more in a moment. OK, I'll illustrate that on quadratic functions in just a moment. Right. So indeed, I would need to look at second derivatives, apart from the case when the function itself is globally convex, right? So if I have a function that doesn't oscillate, okay, and it has this shape, then what I will notice is that any stationary point will be a global maximizer, and I don't have the distinction between local and global and stationarity. Everything is the same, okay? Right. So try to keep this simple picture in your mind, that we are, if a function is convex, then I have no problem. And indeed, if you have an optimization question and you know it's convex, then you can do a lot more, probably, than what I will talk about here. The problem is that convexity, when it's useful for optimization, namely when it's global, it's actually very hard to prove a priori. This is why one of the reasons you need methods for non-convex problems, because sometimes you don't know if your problem is convex or not, and sometimes your problem is definitely not convex. But it happens that you cannot even know this a priori globally. Right. So for convex problems, we don't have these distinctions, and we don't have this kind of oscillatory functions. But but otherwise, okay, if our problem is not convex, or if we don't know if it's convex, right, then to ensure that you are at a minimizer, you need to look at a convexity, local convexity. Okay, what kind of curvature does my function have around x star? And second derivatives tell us something about convexity. So first derivatives is the vector of the gradient is the vector of my first derivatives, and the second derivatives, also called the Hessian, is the matrix of second derivatives. So if I have a function f with x in Rn, then the gradient of f at x is okay, for I from 1 to n, and the Hessian, or the matrix of second derivatives, so this is a symmetric matrix, n times n, if the function is C2, usually is, if you can calculate these. Okay. Right. So I have these second derivatives. Now, second derivatives fully characterize convexity. This is why we go to second derivatives, because sometimes we can, and because they relate to convexity. If this matrix is positive semi-definite, in other words, all its eigenvalues are non-negative. And for example, just think of, if you've never seen semi-definite matrices, just think of diagonal matrices and think that all their entries are non-negative, okay? Then you can show, then you can say that is equivalent to convexity around X star. Okay? And at any local minimizer, we have this kind of local convexity. The reverse is not true. Here's an example. You can think about it later. How about the reverse? If I have a stationary point where all the eigenvalues are positive definite, then I can guarantee that I am at a strict local minimizer. I'm at the local minimizer. The reverse is also not true. You can have an example there. So, but essentially, what I want to say is, first derivatives tell us something about stationarity, and second derivatives tell us something about curvature. Okay. And the other issue is convexity. When we have global convexity, we don't need to worry about local solutions, and we need local convexity to guarantee minimizers. Okay, here's an illustration on quadratic functions. So I take a quadratic function, simplest case of nonlinear functions, right? I take a quadratic function here. G is a vector that's given. H is a symmetric matrix that's given. If I set the gradient of Q to 0, you can verify at home that this is just Hx plus G equal to 0. So H is given, G is given. So this is a linear system of equations in X star. Okay? Assume that H has no 0 eigenvalue. It's invertible. Then there is a unique stationary point. So a quadratic, in general, when it's not degenerate, will have a unique stationary point. Now, what kind of point is this? All right. Right. So based on the second order criticality, what can I say? Well, if the matrix H has all its eigenvalue positive, then I have a convex function and I have a minimum. I have a global minimum. So that's the situation there. And these are the corresponding contours if I plot this in the 2D plane. If H is negative definite, then I have concavity and I have a maximum, global maximum. And again, the contours look similar. I can't distinguish on this plot because it's black and white. If I had colors, I could say if it's a maximum or minimum. Okay. Now, if I have positive eigenvalues and negative eigenvalues, that means I have directions of increase and decrease. That gives me a saddle. You can see here that a saddle point is a stationary point where along these directions I'm convex, along these directions here I'm concave. That's a saddle. And then you have this kind of typical contours. And then you have the degenerate cases of 0 eigenvalues where you can have a line of minimizers or maximizers. Okay. And then you have to be a bit careful with solving this system, okay, because then you will not have a unique solution anymore. But assuming you have consistency, then you have this line of minimizers. Okay, so maybe keep in mind some of these simple illustrations here. So this is your 2D convex landscape, concave landscape, saddle, okay? And then why do we care about this kind of characterizations? Because to any nonlinear function, you approximate it by something simpler, as we'll show in a moment. For example, you can think of any nonlinear function approximately locally looking like one of these quadratics. Okay. Methods. Again, still very general, but we'll get concrete in just a moment. We have a generic method for an unconstrained problem. You have some tolerance. You want to solve your problem to some tolerance. You have an arbitrary guess in Rn. Until, say, the gradient is sufficiently small, I'm going to generate points xk in Rn such that I strictly decrease f at my point. Okay? My next point. And how I generate this is based on problem data, say gradients, all right? Then I take my next point, I check my termination, and I keep iterating. you could also maybe verify some kind of eigenvalue property if you want to ensure that you actually have a minimum. But usually what codes verify is decrease in f and some small gradient. Now, what is the main idea of all the methods that I will talk about is the following. At a current approximation xk, I will, approximation point xk of my x star, I will approximate my nonlinear, nonconvex complicated function by something simple, by a model, by a local model. And this local model can be linear or quadratic based on how much problem information I have available to construct it. Okay? In particular, if I have derivatives, then I use very often Taylor models. So this is just models coming from having derivatives. So a linear model will correspond to having gradient information about f, and quadratic having gradient and possibly second order information. So that means that if you give me a point xk, I can give you with some routine f of xk, grad f of xk, and the second derivative possibly. That's for the second derivative case. So if you look at this simple drawing that I put here in 1D, when I talk about linear models, I talk about approximating my nonlinear function by, say, the tangent. That's a linear model that uses the slope. Or by a quadratic that uses local quadratic that uses the gradient and the second derivative information. Okay? Right. So I approximate at every xk, I approximate my functions based on the information I have. And then what I say is, instead of minimizing my complicated function f, I'm going to minimize one of these simple models to get the change in xk. Things are not so simple, but that's the first thing I'm going to do usually. Right. What things can we ask about, and what things can we guarantee? Well, though the problems are non-convex, actually we can guarantee a lot, surprisingly a lot, I would say, given the generality. So from any arbitrary starting point, we talk about global convergence. This is what you'll see in many textbooks. That doesn't mean convergence to the global minimizer, okay? Very confusingly. That just means convergence. That just means that from any starting point, you will get stationary points of your problem. All limit points will be stationary, or at least one will be stationary. Sometimes we cannot guarantee global, but we can guarantee local convergence. If I'm very close to the minimizer, will I get attracted to it? Okay, that's sort of that's local convergence, and these are not necessarily so useful results because you don't know a priori what does it mean sufficiently close. So you can't really guarantee good behavior of your method, generally, of a solver based on just local results. And most importantly, if somebody tells you, yeah, I know my method converges, if you let it run forever, right, this is what we mean by convergence, it will eventually get there. What you really want to know is, if I sit in front of my computer and I give the solver an accuracy epsilon, how long do I have to wait until my problem is solved? Okay? What these convergence results tell you is that, yes, there is a finite end for any epsilon, your algorithm will terminate finitely. But the speed of this convergence we try to capture it by these global or local complexity results or rate of convergence results. These are equivalent notions. So not just that the method converges, but we care about how fast it converges. And why do we care about? So just, again, some basics. You probably have seen this, but the terminology difference between fields here. In optimization, we call linear convergence a sequence where you can decrease the error by a fixed fraction on each iteration. So here's a 0.5 to k goes to 0 linearly, right? It decreases by, this sequence decreases by 0.5 for each k. Quadratically, 0.5 to 2 to the k, this is quadratic convergence. The error decreases exponentially. Okay, this, I get multiples of 2 correct digits per k. And then we have this sort of intermediate sequence that also goes to 0, and it goes to 0 superlinearly. And here in this plot, I plot k versus log of these sequences. So log of 0 is minus infinity. So they all go to minus infinity, right? But here's the quadratically convergent sequence. So to get to value minus 300, say that's my epsilon, then I take, I don't know, 10 iterations. The superlinear, I get 70 iterations. And the linear, you know, I'm going to get much more. I'm going to take much longer. Okay? We'll mention these rates later on. This is why I'm mentioning them now. And you can see here sort of the rate at which the error decreases. Linear rate, okay, having said this, having shown you how fast quadratic is and superlinear, I should say that linear rate in principle is not a bad rate. Okay? That is not a bad rate in an absolute sense. Okay? But it becomes bad when this factor is not like 0.5 here, but something close to 1, as we will see in just a moment. But besides these rates, we also have something called sublinear rates, which are slower than any of these. But if you're far away from the solution, essentially you will see sublinear rates. Okay, methods. Okay, do you have any questions so far? Okay, it's a bit basic now, but we'll get into it right now. Right. So I will talk about two main classes of methods for unconstrained optimization: line search and truss region. They are the state of the art. All codes out there essentially implement these methods. Okay. So I want to give you the key ingredients of these methods and sort of some idea on their behavior. I will tie in with whatever is said in a moment. Line search methods, generically, in the previous framework we had, okay, this is all the same. I'm going to generate a descent direction Sk that satisfies this property. Then I'm going to compute a parameter alpha k that's going to tell me how far along Sk I go to decrease f. Okay? Remember the fact I've already stated. If this is true, then I am guaranteed to have an alpha positive such that this is true, right, provided it's sufficiently small. Right. So this Sk is the direction in Iran, and this alpha is a positive scalar. Now, I will start by talking about how to compute this alpha for any descent Sk. Right? So this is my key ingredients: a direction and a step. The step just controls how far I go along my descent direction. Why do I need a step? Why do I need alpha k?
If you go too far, you might not guarantee that you're really decreasing.
That's right.
If you go too small, then it will take a long time.
Yes,
to get
very
to
good.
the-
Thank you. Yes, indeed. So we'll see that in just a moment a bit more. So now let's think, how would I just calculate this alpha k? So assume I have my Sk. How would I calculate it? Well, there is something called exact line search, which just means that I will actually minimize my function along my direction Sk. So here's contours of a quadratic. Okay, here's my point, and here's my direction. So now what I'm saying is that I'm going to restrict my function along this direction, and so I get this kind of plane intersected with my surface, and I end up with this univariate function of alpha. I minimize this to find my step here, and that's how far I will move along Sk, and so if I return to my function, that's where I will go next. Okay, this is for quadratic functions. We have an explicit formula. Yes, we can do this. Great. But we cannot do this for non-convex functions. So this is sort of the reference line search, but you don't ever really do this. What you do is something called inexact line search. And as your colleague has just said, okay, we want two things. We don't want the step to be too small, and we don't want it to be too large. Right, so here's a simple quadratic. All right, I start here, and I can give you a formula. I have a step here, and the idea is, OK, you're telling me, I know my property of descent. Right? I know that if I stay close to my Xk, I will be able to decrease my f. So let me take small steps. Okay? So this is what this method here does. It's a step that converges to 0, a step alpha k that converges to 0. So what you see that happens is that your points converge, fair enough, but they don't converge to your stationary point at all. All right? They get clustered together, and they stop before you've reached the region you want to go in. So you say, OK, fine. So let's be more daring. Let's take long steps. So here, I start at this point, and I really take long steps here, right? I move to the other side. Then I move back, right? In this space of my x, this is a very long step. But again, what do I notice here? So this step is for sure bounded away from 0. It's like 2 plus something, right? So I take a long step. But what happens here? Well, I get long steps here, but they are shallow. They don't give me much decrease here. So the step is long, but the corresponding function decrease is small. And in fact, that function decrease goes to 0. Okay? That is also not good, right? So I want to design steps that are not too long, but also that are proportional to the decrease in f. All right. So I didn't want to get too technical in this. What do we require? We require that f goes down from fxk by some kind of sufficient amount. And this sufficient amount is proportional to the length of my step and some problem information. And the usual thing is this kind of angle here. In particular, we have the so-called Armijo condition, where, of course, we look along this direction as k. So I have something that's a function that depends on alpha here. And what I require in this condition is that the graph of my function phi along sk, this graph here, lies below a line. Okay? And this line here, trust me, is just fxk plus some parameter alpha k, and then here is exactly this term. So essentially, what do? I look at the graph of my function phi, so f along sk, and then I look at, this is the tangent. Then I shift my tangent at an angle with beta. I move it with beta. Okay? And then I say, I want to choose a step size that allows my phi to be below this. Okay, alpha equals 0 satisfies this, right? But that's not, of course, I'm not going to choose it to be 0. But anything that's below this will be fine, actually. Anything in here will be fine. There is an error. It's not 0.8, 0.9. Anything here will be fine. And in fact, if I had my function oscillating, anything, I get this kind of disjoint intervals. Okay? If I look on my function here, I could get a line. I will always get a line that goes like this. And so I will have a set of acceptable intervals. Okay? This is what I will end up doing. I will end up choosing a step in one of these intervals. And so what you do in your solver, and this is really what solvers do, is you take this kind of condition called the Armijo condition, and you start with some step size, alpha 0, say 1, and then you cut it until you manage to satisfy this Armijo condition. This you do at every iteration. Okay. You compute your descent direction, and then you do these kind of procedures to calculate your step. It's adaptive. Okay? And it costs me something, right? It costs me because every time I check if I satisfy this, I have to calculate f at the new point. I don't need derivatives, but I need new evaluations of f. Okay? But the adaptivity definitely helps. All right, in performance. Right. Now,
is it something that people use in machine learning, like in deep learning? So they always talk about tweaking the learning rate, and nobody really knows how to do it. But is adaptive?
So this is one thing that we can have more discussions at the end. People in machine learning, they did not know about these things very much, and also you can say that sometimes it's too expensive to do this. Okay, so I'm a big advocate of these adaptive step sizes because we know that they will help your performance. So if you can afford it, this is definitely, I would say, something to consider. There are many reasons people in machine learning don't use specifically this. One is if you use stochastic gradient, you have to control the variance, so you have to let your step go to 0, or I don't know, I haven't seen people trying this. I don't know. I mean, I'm sure you could control it with something like this. In fact, I know because we have other variants that can do this for stochastic problems. But people have tried sort of simple things. And the other thing that people say is that you should choose a fixed step size, like inversely proportional to the Lipschitz constant of your gradient. But that, again, that is definitely too small. That, you know, if you, first of all, you may not have your Lipschitz constant. I never in here assume you know anything about your problem like a Lipschitz constant. And it's definitely, adaptivity is preferable to a fixed step size. Okay. But good question. We can talk a long time about this, so let's right. Okay, so now I want to start talking about directions. So what are good descent directions? So I've given you some general ways to compute a step size. What are good directions? Well, we've already mentioned the negative gradient direction, and that gives you the method of Cauchy from the 19th century called steepest descent. Okay. And why is it called steepest descent? Because I don't know if you maybe thought of this as for the negative gradient. The negative gradient is the direction of the fastest local rate of change in your function. The fastest, the direction of the fastest decrease in your function locally. Okay, and this you can prove by looking at this Taylor first order Taylor linear approximation of your function along xk. If I minimize a linear approximation of my function around xk over all possible directions in Rn, the solution of this problem is the negative gradient direction. Okay. Why do I put this constraint here? Why do I say the length of S has to be something?
You can make it 0.
Sorry?
You can make it 0.
Not 0, but something else. That's not good. Minus infinity, that's right, because this is a linear model, right? If you think of the tangent I drew here, right, this goes to minus infinity. So if I didn't have something, a normalization constraint, this wouldn't be per se well defined. But I can have anything here, you know, it will still give me a multiple of the negative gradient as the solution of this problem. Okay. So a linear approximation, a linear model around my current xk gives me, a linear Taylor model gives me essentially the negative gradient direction. So if I approximate my function by this linear model locally, essentially I move along the steepest descent direction. But I need more than that, like I just said. I need the line search to guide me to ensure convergence. And indeed, here's a theorem. Steepest descent method with exact line search or with Armijo-like conditions will give me a convergent method, provided I have a Lipschitz continuous gradient. Okay? Bounded below Lipschitz continuous, no assumption on convexity whatsoever, no assumption on how degenerate my landscape is. I can guarantee that all my gradients go to 0. So this is indeed a very large class of problems and very weak assumptions. And the Armijo condition is key because you can show that under these assumptions on the Lipschitz continuity of the gradient, that line search condition gives you that the step size is bounded away from 0. Another thing I want to emphasize is why I want to say once more why we need this kind of sufficient decrease condition. You could design a method that you just say, I just want my function to go down at each step. However, you need to not just have this descent direction, right? What can happen is that if I have the contours of my function, okay, if I have the contours of my function, and I have my gradient direction pointing down, negative gradient, right? Then, or any direction, okay, that's descent, what can happen is that even if this angle is not 90 degrees at every step, with every iteration k, this could become more and more orthogonal to my gradient. Okay? Another way to formalize all this Armijo condition is to say that what I really have to be careful about is that the angle between the negative gradient and my search direction, it doesn't become close to orthogonality. This will definitely stop your method from converging. Yes?
I have like a very large Lipschitz constant, so it can vary a lot within quite a small region. How do you see the Armijo condition kind of backtrack, right? Like, how do you choose like almost like the step size you check your?
That's a very, very good question. That is a very good question. So you have to start with something. So people usually start with, say, 1, okay? But there is no prescribed value. So you may want to slightly tune that if you can try your problem a little bit. You can help it start at maybe a better point. Another thing that people do is to actually take a few function samples or maybe a few steps and then use like some kind of local interpolation of your function around the starting point, and then choose your first step size in your line search procedure based on that. That is if you want to optimize, how many steps you spend early on. You can always do it. You can do it with anything, but it may make your method a bit slow. So you may want to do a little bit of tuning early on for this initial choice. Another alternative is you have more sophisticated line searches. So usually, in addition to Armijo, people add something else. And that also helps you with this kind of question, what should you choose as your first condition? But that is only really a problem for gradient descent methods. For second-order methods that we'll talk in a moment, there is a prescribed step size that you always have to try first, and that is the step size of 1. We'll see in a moment. Yes?
So am I right that the key reason of looking for the steepest descent is this convergency concern, right? If you don't do that, as you go along, you might end up into a situation that you kind of trap into somewhere that you never converge.
Right. So this angle condition will never be a problem for the negative gradient direction.
Okay.
Because the angle between the negative gradient and the negative gradient is always 1. So this problem you will not have for steepest descent, but you will have it for other line search methods. So in your line search methods, whatever you're using, you have to be globally careful about this.
Yes, but the steepest descent is really the steepest.
Yeah,
right?
so this will not have this problem.
I'm thinking, could there be a even clever method that would take into account, because when you go, if your next step is the steepest, it doesn't mean that overall you're really going to the place that is lowest.
Yes, so
right?
yes, it's coming,
So,
okay.
All right.
Right. The problems with steepest descent, okay, is scale dependent. So first order methods, and this is, gradient methods have this major problem, and this is one thing that I think is not known enough and not emphasized enough. What does it mean that the method is scale dependent? What does it mean to have a problem that's scale dependent? Okay, so that means that that's ill conditioned. Okay, a problem. What is an optimization problem that's ill conditioned? That means that I have some kind of process that I'm trying to optimize, like a chemical reaction. Some components in that process happen in minutes, and some react in hours. All right, so I have fast varying components and slowly varying components in the problem, right? So that usually gives rise to an ill-conditioned problem. Now, what happens is the steepest descent inherits the ill conditioning of the problem. Okay, it's not immune to it; it inherits it. So here's a quadratic example: 1/2a x1 squared plus x2 squared. A is a parameter, right? Now, this problem, I can make it ill-conditioned, right? So I can make the contours of my quadratic to get like this. So they are long in this direction, slowly varying in this direction, and fastly varying in this direction. Okay? How do I make this? So you can see that if A here is large, say 1,000, ill conditioning is defined as if I move a small distance along x1, f will change by a large amount. If I move the same distance along x2, f will change by a much smaller amount. That's a typical ill-conditioned problem. Now, what happens to steepest descent? I have this, I have notes that I can give you if you want. The steepest descent the number of iterations it takes to solve your problem will be dictated by the conditioning of the problem. Okay? The rate of steepest descent is fundamentally linked to the conditioning of your problem. And here's an illustration of the iterations of steepest descent with exact line search for, I don't know, mild ill conditioning. Now, I rescale my contours so that here I put 1. So I have this perfect scaling. The steepest descent terminates in one step. Okay? So the behavior is very connected to the conditioning of the problem. And here's the Rosenbrock function. We started with Rosenbrock, with this banana-shaped valley. Here are the contours of this function. Steepest descent with backtracking Armijo, yes, you have a perfectly Lipschitz gradient. You have absolutely no problem with that. However, steepest descent is so slow in converging that it breaks down due to accumulation error, and actually you stop seeing it converge. In theory, this converges, but the rate is so slow. What is the rate? The rate of steepest descent close to a minimizer, close to a stationary point, is linear. That in itself, despite what I'm saying here, is a good rate. The problem is that the convergence factor in the linear rate is very close to 1. Usually. This rho here is as follows. The rho, the linear factor in steepest descent, is the condition number of the Hessian at the solution minus 1 over the condition number plus 1. Okay? That is, you can prove. This is the provable upper bound on my rate. And there is a classical paper where the author shows that actually this rho, though this is usually something you upper bounded by, is attained on many, many instances, usually attained. So this means that this is what dictates the conditioning, my Hessian, my second derivatives, right, the curvature there, the conditioning of that matrix. And you can see that as k grows, right, this rho approaches 1. And that's actually the rate you see usually for steepest descent. Okay, so this is not good. So you have this scalar dependence connectedly to rate, slow rate, even close to a solution. So what should we do? What do we do if you have a problem you want to solve and you know it's ill-conditioned? What should you do before you give it to any solver? You should scale your problem. Okay? You should, if you know that some of your variables vary in kilometers and some vary in meters, you should give at least a simple scaling, rescaling, so that everything is measured around the same kind of units. Okay? Right. Now, what can we do in methods? We can rescale the steepest descent. Okay? So, it's very important for a good method to scale steepest descent. All right? So, I take a matrix BK, symmetric and positive definite. And now, in my generic line search method, I'm not going to take the steepest descent. I'm going to take a step sk that is the solution of this system. Okay? So now, I've what have I done though? I've made it, I've made, before I just computed the negative gradient. Now I have to solve a linear system to compute my direction. So the cost has increased. But if bk is symmetric and positive definite, sk is minus this times the gradient, you can show that this direction is descent. Okay, this is why you need a positive definiteness. If you don't have it, you lose the descent property. Okay? Furthermore, you can show that if, again, under this assumption, so that this quadratic function here is convex, then this direction minimizes a second-order approximation of my function around the current point. So to solve my problems with steepest descent, I've gone to second-order models. I'm starting to take account of the curvature, because if I'm blind to the curvature, I get into serious ill-conditioning problem and slow rates. So now we have this, this is S. This should be S, sorry, not SK, S. So now I'm going to, my direction here represents the minimum of a convex quadratic local model. Okay, so what are good choices for BK? If I have second derivatives, then I can choose for my BK to be exactly the second derivative matrix, if it's positive definite at xk. And then we get Newton's method for optimization. Right? That's Newton's method for optimization. Furthermore, Newton's method, as you may know, has this amazing property that it is affine invariant. So if I have that, I can show that even if my problem is ill-conditioned, the method will not be affected by conditioning of the problem. That is the amazing property of Newton's method. Of course, I only mean here affine transformations of variables. Okay, I can't give it, I don't know what crazy nonlinear transformations and expect things will work well. But with respect to linear changes of variables or affine, Newton has this property. And so we gain affine invariance, and we gain a fast local rate with it, namely the famous quadratic Newton rate of quadratic rate of Newton's method. Okay, so we've gone from bad linear rate to quadratic rate locally. We've gained affine invariance. What have we lost? We lost global convergence. So we had global convergence with steepest descent, right? From any starting point in theory I could prove, okay, for very general class of functions. Now, for this kind of methods, I need much stronger assumptions to be able to guarantee convergence, at least for this kind of line search methods, line search framework. So this first line is the same as for steepest descent. I have a sufficiently smooth function, a Lipschitz continuous gradient. Now, the matrices BK have to be uniformly bounded above. Okay, that's not maybe such a big deal, but uniformly bounded below, away from 0. Okay, I've simplified the language here. Eigenvalues of BK uniformly bounded away from 0. That means convex, and it cannot even get close to singularity with K. So very, very nice convex local models. Then I can guarantee that that all my limit points are stationary. So I need local convex quadratic models. And for example, if BK is my Hessian, my second derivative matrix, then I need local convexity at all my iterates. How am I going to know that, right? I can't really know that in advance. So I can't really apply Newton's method with line search like that generally, because I will not necessarily have local convex models. So that is my problem now. Okay, so now I have to fix this problem. I have to fix global convergence for a more general class of functions. And let me just say this, you will see this happen. I can give you simple examples where Newton is going to fail from arbitrary starting points. And Newton with line search is going to fail. So not only that you will encounter negative curvature, but if you don't do line search, you will definitely fail. So this is a real problem. Okay, this is, sorry. Right, so on Rosenbrock, Newton with line search, if you have local convexity where Newton is going, then you get quadratic rate. But if you start from other points, you're not going to get local convexity of your models. So then what line search methods do is they perturb the Hessian by some matrix. And on every iteration, say you try to, so this is what you do. You have to come up with an MK that perturbs your Hessian so that you can make a descent step. Because line search methods say you have to take a descent step at every iteration. And so you have to make this matrix positive definite to secure you can do a line search and you can get this strict descent. So what do people do? I mean, these are technicalities. You don't need to follow them. Usually you try to, so to compute SK, you have to solve a linear system. So what do? You factorize your matrix, let's say, right? You use Gaussian elimination, in other words. The fancy name for it is called Cholesky for a symmetric matrix, because you are actually going to store the factors and do something clever in the linear algebra. This will only, the Cholesky factorization will only work if your matrix is positive definite. So you start applying it, and you notice, like in Gaussian elimination, you get 0 or negative pivots. You permute, you try to get a positive pivot. You can't. You conclude your matrix is not positive definite. And then you introduce a small perturbation to your pivots to make, that makes the resulting matrix positive definite. You just perturb your pivot to give you a positive pivot in Gaussian elimination, and you continue your factorization. That implicitly gives you this MK. Alternatively, you can use some method to compute the smallest eigenvalue of lambda min, the smallest eigenvalue of the Hessian, some lambda min, and then perturb here by minus lambda min plus some small epsilon. There is some numerical problems with that, but it's done as well. Right, so there are various tricks. I don't have time to decide. This is very popular with Cholesky, but you know, now people are very keen on smallest eigenvalues of Hessians and so on. So they are starting to do different things. So you have to fix this. So now you can show that, you know, this is what line search codes do. They have to do this and check this and try to fix the Hessian if they calculate the Hessian. Okay, I want to mention another class of methods for approximating the second derivatives. So when you don't have second derivatives, but you have gradient information, you can have these quasi-Newton methods. They are called quasi-Newton methods. And these are methods from the 60s, but they are really clever. And one method in this family is very much the state of the art for unconstrained optimization. You start with some initial guess of your second derivative matrix. And it can often be, and it's OK for it to be, the identity matrix. So that means that your first direction, you know, at S0 is steepest descent, OK? And then you compute your next iterate, just like before, with line search. And after you computed your iterate, you're going to compute a new approximation, bk plus 1, of your second derivative matrix. And of course, you would like this matrix bk to sort of approach, sorry, this should be x star, approach the Hessian at the solution, and to contain some kind of curvature information along the way. So this gives rise to these quasi-Newton methods that are really sitting between steepest descent and Newton. So what do people do? What is the crucial ingredient here? So I said that you want to capture a curvature information. Now, if I'm at my point xk, I have gradient information. Of course, I could do finite differencing if my function is smooth to estimate my Hessian. But then I would need n gradient values, you know, where n is my problem dimension, to estimate my Hessian well. These methods estimate your Hessian from just one more gradient information. So you compute xk, and after you compute your xk plus 1, you already have this gradient at xk. You compute the gradient of f at xk plus 1, and what you require from your new matrix bk plus 1 is that it matches the change in curvature. So you require that bk plus 1 applied to your change in iterates satisfies the change in curvature. This is satisfied, for example, if f exactly if f is quadratic, right? But this point xk plus 1 is not going to be, very close to xk, right? It's your next iterate. So it's really a secant idea. All right. But it captures this kind of curvature information. There are many ways, because this equation is just n, right? So I'm finding bk plus 1. bk plus 1 is a matrix, it's a symmetric matrix. But still it's going to have order n squared unknowns in it. So just satisfying this equation, which only has n equations in it, okay? This is a linear system in bk plus 1, but it only has n equations. So I can't find all of my bk plus 1 from this secant equation only. So I need to impose a bit more. So usually you just say, well, I want bk plus 1 to be a cheap update of my bk. And the usual way is to compute bk plus 1 to be a rank 1 update of bk or a rank 2 update of bk plus 1, or a rank 2 update of bk. And then this equation is enough. And you obtain the formula of, say, symmetric rank 1 when you do a rank 1 update, or BFGS when you do a rank 2 update. And you gain two more things. You gain that you can use clever ways of calculating the inverse of your new matrix, so that you do not have to solve a linear system to compute your sk in the next iteration. You only need to do a new matrix vector product. So you reduce the cost of your iteration, okay? And you also gain the fast rate of convergence of superlinear convergence. So it's not as good as quadratic, not as good as Newton, but better than steepest descent. And you can show affine invariance properties in certain norms. BFGS here, a limited memory version of it, is considered very much the state of the art for unconstrained optimization. And you only require gradient information for it. You have to be careful with your line search, though, because you can't do backtracking Armijo. You have to be careful because you want to maintain positive definiteness of your updates. That's the BFGS update. You want to maintain the matrix BK to be positive definite. And just Armijo will not do that for you. You have to impose another condition called Wolf condition. But this is all well-known stuff. You can find it in the recommended bibliography at the end. All right, so these are really clever methods, and they have not gone out of fashion. OK. Going beyond line search, something called trust region. All right? No, it's not used in machine learning, but it should be. OK? So, right. What is the problem with my local models? OK? Is that my function is non-convex, right? So if I approximate my function by a quadratic locally, I'm going to often get this local non-convex quadratic model, right? And then what do I do with my line search method? I convexify it to make sure I can take a descent step. So I impose this convexity to non-convex landscapes. OK. Sophisticated heuristics exist. Line search works. But there is another alternative called trust region that allows you to have non-convex local models, and it deals with them in an automatic way. So that's one thing about trust region. And the other thing about it is that you don't need to do the line search anymore, in the sense that it will give you descent in your function eventually. OK, so now I'm going to take this model, this quadratic model with bk here that can be closer to my Hessian or not so close to my second derivative, whatever I can put in there. This model is, first of all, not bounded below if my bk is not positive definite. Okay, so I can't even talk about minimizing it properly. Okay, and also, it will not resemble, of course, my f if I'm too far. So what we do here is we impose a condition on the length. So I say that my Sk has to be less than delta k. So what do we do in that? So what we have here is that I put a ball constraint at my current iterate xk. I put a ball constraint. And that's the same, right, as s less than delta k. Right. Now, once I do this, I have this. Now, instead of computing my sk, right, from minimizing linear, quadratic, and constraint, I constrain my model. Okay. So this mk, it can be first order or second order model. Think of it with bk, subject to this constraint, this ball constraint. Right. So now, because of this ball, a ball, right, is a bounded and closed set. So this model, which is a nice continuous model, is going to always be bounded. But it may be non-convex. But now I've added constraints. So this becomes harder. But it's actually, you can make it work. So here's a plot. So I have here, these dashed contours are the contours of my underlying nonlinear function. Then I have my current iterate here. And these are the contours of my local quadratic model. Okay? And this black thing here is my ball truss region constraint. All right? So now I'm going to say that now I'm minimizing this quadratic over this ball. Okay? Where is the solution? Right? The solution in this particular case is this global minimizer of my quadratic. I have a question for you. What is this global minimizer of my quadratic in this case? How do these contours look to you? What kind of function? What kind of model is this? Quadratic, convex or non-convex? Convex. So I have a nice convex local model. And I'm saying that I can see that, of course, the global minimizer of this model is inside the truss region. Okay? So what if I were to minimize over the ball, I would just get this point, of course. Right? What is that point? From what we've been discussing, what direction? Venture a guess.
What's the stationary point of the model?
Yes? What is the stationary point of the model in this case? Well, it's hard for you to know, but OK, maybe. Let's say that. It's the Newton direction. So think of it like that. So if this is the second order true Taylor model, is the Newton step. OK. So you can take the Newton step if that Newton step is inside my truss region. Then, OK, I can have a linear local model, linear Taylor local model, and then you can see that, of course, the linear model is always unbounded below, so the minimizer is always on the boundary of the truss region constraint. Now I have another kind of local model at this point. You can see that it's still quadratic, but this one is not quadratic. Sorry, I'm saying no. I mean, it's not convex. It's quadratic, but it's not convex. And then you can see that if you look at the colors of the contours, you're going to get the minimum of the model over this ball somewhere here. Okay? And on the boundary, definitely on the boundary. And here we have a convex local model, quadratic, and the full global minimizer is outside of the truss region. And so again, the minimizer is going to be on the boundary of the truss region constraint. I'm giving you these illustrations because it turns out that we can calculate the global minimizer of this non-convex quadratic subject to the ball constraint. We can efficiently calculate it even for large-scale problems. And it has this nice feature that it is the Newton step. the global minimizer of the trust regions problem is the Newton step of your problem if you have a quadratic model, convex, and if it's inside the trust region ball. If not, you're going to cut it, up until you satisfy the trust region constraint. Okay? But it also allows you to deal naturally with the non-convex local quadratic model. It automatically gives you a perturbation of the second derivative matrix that makes your step descend. Okay, it's a lot more to say. This is not so simple, but I don't have time. Okay, so how do we measure progress? So now we don't have the line search anymore. And what do we do? In these problems, we minimize the model from its value at s equals 0, namely from xk. And then we look at the actual function decrease at the new point. And we measure this relative ratio. Function decrease versus model decrease. This denominator is always positive. But the numerator may be negative. There is no guarantee in trust regions that at the new point, I'm going to go down. So if this is negative, okay, then what can I do? It means that I've gone too far when I try to minimize my model. And all I can do is shrink my trust region radius. So I'm going to stay at the same point xk and shrink my trust region. All right? And resolve the model. The model stays the same, but the trust region shrinks. And then I resolve this. So trust region does not give you decrease strictly on each iteration. You have these steps called unsuccessful steps where you may not make any progress. But it doesn't cost you additional gradient evaluations or Hessian evaluations because you keep the same model. But it does cost you one function evaluation because you have to check the row. Right? What is the connection here to Armijo? This row here, if M was a linear model, would be exactly an Armijo-like condition. But you don't have any line search, so this is what you do. Right, I will show you an illustration in just a moment. So what can we show about convergence here globally? These methods work globally. You don't have to minimize to the global solution of the trust region subproblem to get good behavior. You have a very weak requirement that in which you say, I'm going to minimize my trust region model. Okay, so I mean minimize model subject to trust region constraint. I'm going to minimize that so that I get as much decrease in the model as if I had taken the steepest descent step. Under that weak assumption, you can prove global convergence under the same assumptions as for steepest descent. But what is this result hiding? It's hiding that I can take whatever step minimizes my model. I can take the Newton step. I can take second order steps. I can take anything. So this is a very flexible framework that allows me to deal with non-convexity. All right? And yes, I've made my subproblem more expensive, more difficult to solve. But we have various techniques. If you can factorize this matrix, we have very, very efficient techniques. If not, you can do Lanczos kind of methods, CG, conjugate gradient kind of methods, to solve large-scale problems. Okay? So definitely, in your implementation of trust region, you go beyond steepest descent. You're not going to take steepest descent steps unless you are in some kind of trouble and you can't do anything else. You're going to have some kind of curvature information coming in. So let me tell you an illustration of how this method works. So we have here a non-convex function that has two minima, two local minima. And here are the contours of this function. I'm going to run trust region on it. I'm going to start at a point fx0, 97. All right? My point is here. Okay? And my contours of my quadratic model at this point are in the right-hand side picture. So I start from delta k equals 1. All right? I have a direction because here I am. Here's my now, so contours of objective overlaid with model contours starting point, okay? Trust region constraint. I minimize approximatively the model on this. I get my next point there. Right. So that's my SK. Means that is this minimizer here? Well, minus xk. Right. That's my function there. So I compute my rho, the change in f over the change in m. And I get something close to 1. So the change in f is a positive multiple of the decrease in the model. That's good. That's a good thing. My model decreases, my function decreases almost as much as my model. So then I take my step. And I say, OK, this is good. It means I have good agreement between model and function. So I'm going to allow, in fact, my trust region to increase. So I go to this. So I've moved at my next point. I've taken the step. But I've also enlarged my trust region radius. Because if you always shrink it in the course of the algorithm to make progress, you will end up having very slow progress. So now I'm here. Again, I have a quadratic local model. And now I minimize this approximatively, very approximatively. So I go here. So I look, wow, now my rho is even larger than 1. That's very good. So I take my step. I increase my trust region radius. So I've moved to this point. And now this is my current iterate. So what kind of contours do I have? Quadratic, but non-convex, right? You have a saddle there, or close to a saddle point. And this is now my trust region is huge, all right? So I minimize my model approximatively, right? And what do I get? That my rho is negative. So at the full step here where I've minimized my model, my function is going up, not down. That's because I've gone too far, right? This trust region is way, way too large. And I have this non-convex model. So then I stay at the same point, and I shrink my trust region radius. I've gone too far. I've trusted this local model, which is accurate if I'm close to xk. But if I've gone too far, it becomes inaccurate. Not a good representation of my function. So I shrink back. I stay at the same point. I keep the same non-convex model, but I shrink my trust region radius. And I minimize again. And now I go to this point here. OK, that's good, because you can see the underlying contours of my function. I'm getting closer, right? So now things have been, we've recovered. We are again going to see these kind of fractions close to 1, all right? And what do we see here? What happens to the contours? The contours are quadratic and very nice quadratics, all right? And my trust region is large now. It's somewhere here. And the global minimizer of this quadratic is here. So I'm taking Newton steps. I'm taking Newton steps. I'm getting good decrease. This trust region becomes irrelevant. And I keep taking Newton steps. Okay? And this is typical when you get close to a non-degenerate minimizer. Your trust region becomes irrelevant. And you take just good steps. And you are allowed to take the Newton steps. And you get quadratic convergence. You can prove you get quadratic convergence with trust region. OK, so that's it. We've gotten there. Of course, this was getting to this local minimizer. But now if I initialize somewhere else, I may end up at the other minimizer. And this remains the feature of these methods. These are local methods. You use derivatives. You use gradients. You will never be able to guarantee a global solution, convergence. Right. You can use quasi-Newton methods in this framework as well. You can use indefinite quasi-Newton formulas like symmetric rank 1. You don't have to use BFGS. OK. State of the art for non-convex optimizations, you go and get a solver out there. We'll use something like this, a line search or a trust region, a BFGS method or similar, or maybe if you have second derivatives, a Newton-like method. It's a bit of a matter of taste because the heuristics in line search are so well developed that you can deal with local non-convexity. But trust region gives you maybe a more natural way of dealing with these non-convex models. OK. Constraint problems. Right. OK. Don't ask me yet what do you do if you don't have derivatives, because I will come back to unconstrained problems in the last hour. and talk about the case when we don't have derivatives. But I want to tell you a little bit about constraint optimization. Right. OK. Any pressing questions that you really, really have to ask me now before I move on? OK. So I want to talk about these points here, x equals a. OK. These are the kind of points. OK, we have constraints. But if the constraints, this point here is both a constraint minimizer and also an unconstrained minimizer. So for many problems, if you can stay feasible, you end up boiling your problem to an unconstrained problem. But what we really want to find is this kind of points on the boundary. Think you have a linear objective function that's unbounded below, and your constraints are crucial, and all your constraints are nonlinear and non-convex functions. What do you do? Well, the optimization community has spent many years trying to solve these problems. And I think it's pretty amazing what the solvers out there can do. So you have, again, a generic f. But now you have finitely many equalities and inequality constraints. The problem is that I have to go back to basics. I have to tell you how do I characterize those points on the boundaries. The gradient at this point is not 0. Is not 0. So how can I characterize those boundary points in terms of derivatives? OK. The underlying idea of what I will talk about in what follows is that we make everything that's constrained unconstrained. OK? Because we know how to deal with unconstrained problems. So for optimality, we instead of stationary point with 0 gradient, we have this notion of Karushkin-Tucker. Where is that coming from? For every inequality in here, so ci of x equals 0, I'm going to multiply it by a yj, scalar. For every inequality here, I'm going to multiply it by a lambda I multiplier. And essentially, these yj's and lambda j's will help me look at the rate of change. So now I've bundled my objective and my constraints into one function. A Karushkin-Tucker is a stationary point of this function with respect to x. OK. So stationary points of the Lagrangian function are KKT points, provided also that they are feasible. Of course, I only care about feasible constraints. And I also have one more thing that I need to satisfy. I need to satisfy something when it comes to inequality constraint multipliers. If you look at this plot here before, OK? Let's pause here for a moment. At this point, when I look at derivatives, right? Derivatives give me infinitesimal change, give me local information, right? This constraint here, though it's a constraint of my problem, is going to have 0 influence on my point here, because I'm far away from it. The only constraint that blocks me here is this boundary. Okay? A constraint for which I'm an inequality constraint, when I'm on its boundary, I call it active or blocking constraint. You can think of it as a blocking constraint. And we call these ones inactive. And what you must have to secure a KKT point is not just stationarity, but also that only actually active constraints make a contribution in this term that relates to inequality constraints. And we capture this by this property here, complementarity. So in other words, if I'm on this is only for inequality constraints. If ci of x hat is positive, so that means I'm in the interior of that constraint, like before, x was strictly less than b, then the corresponding multiplier is 0. Okay? And vice versa, if I have a positive multiplier, I must be active. In other words, I could have just stated here that this is only over those constraints that hold as equalities at x hat, so namely the constraints for which x hat is on the boundary. Okay? Okay. Right. Also, I have to have non-negativity for inequality multipliers. Right. So what do we have? So if I set the gradient of this Lagrangian to 0, I'm going to get here grad of f this is gradient with respect to x. Grad of f equals linear combination of gradient of Cj's, right? Minus sum of grad Cj's minus lambda I grad Ci. Okay? So this condition is just this condition here. In other words, the gradient of f is a linear combination of constraint gradients. Okay, here's an example. Just look at this picture. Okay, don't read those numbers. Okay, if you want to verify it. Okay, just don't read those numbers. Okay? Sorry. Right. So I have this quadratic. This is my objective. It's convex. Then I have this omega feasible set. I have a parabolic constraint and I have a line constraint. And this feasible set is inside. The gradient of my constraint is here, orthogonal, right? Is for that. The gradient of this constraint, orthogonal, is here. And at this point, which is the minimizer, contours decrease this way. This is the global minimizer. It's actually a convex problem. I have that this is the gradient of my f, okay, my function here. You can see that's the tangent and then the normal. So the KKT condition tells me this. These are both active at this point, these constraints. The constraints are active at this point, right? They are inequality constraints. So the KKT tells me that the gradient of the objective has to be in the cone generated by these two constraints. Okay? If there was no sign restriction on the multipliers, it just says that it's in the span of those two constraints, in some subspace generated by the constraints. But because they are inequalities, it has to be in the cone. Okay. So essentially, what I'm looking for is this kind of alignment. So we'll see in a moment. I'll say this again for just one constraint in a moment. Essentially, the gradient of f has to be in the cone generated by the constraints for inequalities or in the span of the gradients of the constraints for equalities. Okay. Is any local minimizer a KKT point? Okay. No. You have to have some regularity assumptions on your constraints. So I want you to pause for a moment. I'm talking here about the most general things you can have. You could have very, very non-convex constraints. Smooth, but just because the constraints are smooth, when you intersect them, together, they can give you kinks and all sorts of strange shapes. So it turns out that this implication is not true unless you have some regularity assumption on your constraints. For example, you have to assume that you have some kind of interior of your domain. This is very well developed. There is all sorts of theory, all sorts of constraint qualifications, they are called. But still, in codes, people verify KKT assumptions. If in your code you see that your multipliers just keep growing, the y and the lambdas just keep growing, then that's a sign, for example, that KKT may not hold at the point. All right? But, for example, linear constraints don't need any constraint qualification. In fact, the reason you need a constraint qualification is because when you talk about gradients, you talk about linear approximations of your constraints, right? So you have to have that your region is well represented by linearization of constraints. And that's why you need constraint qualifications. OK, this is maybe too technical. Right. You don't need it for convex problems. What is a convex problem with constraints? You can find this in here. If you have a non-convex problem and you want to get guarantees that you have a local minimizer, then you need to go to second derivatives. And now that it gets very complicated. Because what you need is that before we had that the Hessian of our objective, the second derivative of our objective, was positive definite, or you had convexity for the objective. But now you don't necessarily have convexity for the objective. You have convexity for the Lagrangian over feasible directions. So you have two things. You have the Lagrangian that has to be convex, but also that's only true for directions that are within your feasible set, that keep you within your feasible set. your objective, okay, 1D case, all right? One more time. Here, right, this, I'm going to only look along these directions for convexity notions here. That's essentially the idea. So second order, oops, sorry, second order criticality is very difficult, but I mean, I don't have time to talk about it now. Right. Methods. I want to give you two ideas of methods. How to deal with nonlinear equalities, possibly non-convex. Right. So I want you to, in the process here, I want to sort of get a few ideas across. So one thing is that we often will make constraint problems into unconstrained. We already saw the Lagrangian. But it turns out that the Lagrangian itself is a very difficult function to optimize. So you can't quite solve that. Right, so we have to do something a bit different. Now, let's assume for simplicity we only have equalities. Nonlinear, because if they are linear, you should just find a basis and stay feasible throughout your algorithm. When you have nonlinear, non-convex, or just nonlinear, it's hard to get feasible for equality constraints. This is how I want you to think of it. It's very hard to generate an approximately feasible point. This is not trivial necessarily. Furthermore, I want to generate one that minimizes my f. So I will bundle these two requirements into one objective, the penalty function. And here I'm just talking about quadratic penalty, but there are other penalty functions as well. So what do we do in quadratic penalty? We put all the constraints in a norm. So C is a vector, but I put it in, say, an L2 norm, for example. I square the norm, and then I put a weight here of 1 over 2 sigma. The 2 is just because of these two, but 1 over sigma. Sigma is positive. Okay, so what is this? As sigma goes to 0, this term gets larger and larger. So I get a larger and larger weight on this term. So what I will do in the method is, instead of solving my original problem, I'm going to minimize this unconstrained minimization for some sigma. Then, so unconstrained minimization for phi for fixed sigma. Then I'm going to decrease sigma, minimize this again. Decrease sigma, minimize this again. I can prove to you, but I can't because I don't have time, that the stationary points of this function, so grad phi of this, is actually the first KKT condition. Actually, I can give you this right now. Okay. So grad phi of sigma, this is stationarity for my phi, right? Gives me grad phi, grad of f plus sigma jx transpose cx. Okay? 1 over sigma, sorry. J is the Jacobian of my constraints. So if I let 1 over sigma, I put it here, let's say, I let this to be my y, this, okay, is exactly the Lagrangian, the gradient of the Lagrangian being 0 at x, where y is estimated by this quantity here. So the first condition on stationarity on KKT, the first condition on KKT is satisfied by stationary points of phi. What is not satisfied with respect to my original problem?
The second order condition?
Yes, but let's ignore that for now. Feasibility. Okay? So this is why I keep increasing the sigma, because if I keep increasing sigma, I'm going to, when I minimize this, force this term to be more and more important in my phi. So as sigma goes to 0, I will approach feasibility. Okay, here's an illustration. Sigma equals 100. 1 over, yes?
Is the feasibility condition satisfied by the positivity of the multipliers?
No, because I'm trying to satisfy KKT. So that's what I'm trying to get. That's what I'm trying to get. So in the limit, yes, but not, and yeah, not. And here, for equality constraints, those might, yeah, I don't have that. Right. OK, before we go on, why have I squared here? Yeah, to make it smooth. If I didn't have this here, this function would no longer be smooth, right? So in quadratic penalty, we square it to get a smooth function so that I can use derivatives and so on. Right, so sigma equals 100. So my quadratic penalty function, which is, phi sigma equals f plus 1 over 2 sigma cx squared, OK? For sigma small, this is almost like minimizing f. My function f is this simple quadratic, and these contours here, honestly, they look almost like f. So I minimize my phi. This is phi for this sigma. I minimize it. I get this point here. Now, the minimum of my function is here. And it's where these contours are tangential to my, thinking that these are essentially f's contours. This is the point where this, the constraint and the contours share a tangent or share the normal, which is the KKT. Okay, fine. Ignore that comment if it confuses you. So this is my minimizer of my constraint problem, of this problem here. This is where I'm trying to get to. This is the first solution, first minimizer of my phi. I shrink sigma. This is my new phi. OK? The contours start to elongate. This is my global minimizer of phi. I shrink sigma. I shrink sigma. This is my global minimizer of my phi. I shrink it more. The contours of my unconstrained function start taking the shape of my constraint. OK? And because of the way phi is constructed, the stationary points correspond to KKT points, I will get that property. What else do we notice here in these contours? When these contours elongate along the constraint, they will blow up very quickly in this direction. And they may be much more slowly varying along the constraint. So what can we conclude about phi? It's ill-conditioned. It will generally be ill-conditioned. All right. So what other problem may we have, right, is that this was a nice example. But if I have some non-convex, very complicated function, not all stationary points of my phi will, in the end, correspond because of the losing feasibility and maybe not being able to satisfy feasibility to the true minimizers. But in general, if things work well, this actually works. So we decrease, exactly like we say, the simplest framework, decrease sigma, minimize, and we do another thing that we really like in optimization called warm starting. So I minimize my phi for a new sigma. But I've already calculated a solution for the previous phi of sigma. So I'm going to start my new minimization of my new phi from the previous solution. This kind of warm starting really, really, really helps on ill-conditioned problems. This is why on lasso, you should do the same, and people do the same. For example, you always, when you minimize your lasso function with lambda, with some parameter lambda, you start from the previous solution. So this works, and then you can use any method here for phi, line search or truss region. But you may want to scale your truss region because of the ill conditioning. Because if you take, a trust region size that gives equal importance to all directions, then you will get the ill conditioning right inside your subproblem. And so you have to be a bit careful and scale your trust region locally. We can state convergence results in very general frameworks. I leave this for you to read at home. But I want to say something about here. So we saw this ill conditioning. This ill conditioning is real. You will notice it in numerics. When you calculate Newton-like directions, this is where you'll see it, but also in steepest descent directions, because you will see it right away, all right, in your gradient. So the approach that works very well is actually to do some kind of primal dual methods, where instead of just operating with calculating Newton changes to the primal, you also calculate Newton changes to the dual. So for example, that means, this is what I mean, instead of calculating Newton direction for this x, I'm going to calculate the Newton directions for this y. So when I calculate my search directions, I'm going to get a bigger system to solve, but it's actually very good at dealing with ill conditioning. Okay. Break. Can I go 10 more minutes and then break? Okay. Interior point. So how to deal with inequality constraints? So there is a difference. There is a difference between equalities and inequalities. For equalities, we think that feasibility, in principle, okay, feasibility is hard. So we go to these penalty ideas. For inequalities, we think feasibility is not the big issue, because I think, okay, maybe I have some large constraint, a large constraint set. You have inequalities, in principle means you have quite a bit of slack. The problem with inequality constraints is that they bring a combinatorial aspect to the problem. So I want you to think for a moment that you just have f of x subject to a box constraints, right? A hypercube. Your solution is on the boundary. You want to find out which of those constraints hold as equalities, which of your box constraints, which are your hypercube constraints hold as equalities, okay? In d dimensions, this is not necessarily a simple question. This is a combinatorial question. You want to find which ones hold as equalities out of a bunch of inequalities. So in principle, you would have to try all combinations. So this is what makes inequality problems hard. This is what fundamentally makes linear programming hard in some sense, is this combinatorial aspect hidden in inequality constraints. So I'm going to try to give you an illustration as to why we need to go to these kind of methods I will talk about for inequalities. I want you to think for a moment with the simplex algorithm for linear programming. Have you ever done this? Have you ever seen this? Right, in principle. So I just want to remind you. I have a linear objective, linear constraints. Simplex algorithm goes along the boundary of your feasible region. Okay. And you start here, you go here, and so on, and you try to find the one where your linear objective attains its value, its optimal value. In this process, right, you may try all the vertices. In particular, you may try all vertices of a cube, like in the famous Clementi example, and you end up with exponential complexity. And to avoid that, you may want to just avoid the boundaries. Hence the idea of interior point methods. I will come back to linear programming at the very end. So we are going to try to stay feasible with the idea that I don't want to get into this combinatorial business of what constraints are active. How will I do that? This will also make my problem essentially unconstrained. But how will I do this? I'm going to put each of these inequality constraints into a log term as Ci of x inside my domain is positive. So when this is close to 0, log of 0 is minus infinity, with minus here plus infinity. So this term here blows up at every boundary of my domain. So this function encounters blow up at every boundary. That means that the function is very large at all the boundaries, right? And so the minimizer of it must be well inside the feasible region. OK. Right. So it acts as a barrier because of this blow up, preventing me to get close to boundaries. Right. But I want a solution on the boundary. Right? So what do? I vary the weight. So as mu goes to 0, right? So when mu is large, OK, when mu is large, this is what I'm minimizing here, this term. This will be a point that's well inside in the center of my region. Let's think of it that way. As mu goes to 0, I put more and more weight on f. So that will allow me to slowly approach one boundary, namely the optimal boundary. All right. Now, because of the log term, I need to keep this Ci of x strictly positive, right? I need this function to be well defined throughout my iterations. Right. So I need to secure that. But I can secure it without imposing it as a constraint. And so that essentially I can treat this as unconstrained. OK. Right. So that's the idea of these barrier methods or interior point methods. Stay strictly feasible to avoid the combinatorial aspect. This is what I've explained. Of course, we may have spurious solutions. But let's look at an example. So now I have a similar quadratic objective with this kind of inequality constraint. 0, the origin doesn't satisfy it. So it's this region here. OK? And the minimizer is somewhere on this boundary. And this is my log barrier function for mu equals 10. So this, you can't even see the blow up. The blow up is very bad here. OK? You can't even plot it properly. It's very sharp at here. The minimizer of the log barrier is somewhere here, far away from my boundaries and so on. I decrease mu, it's starting to approach the boundary. A minimizer of my barrier is there. I decrease mu even more, right? I'm getting closer and closer to this boundary. Okay. Here you can't even see all of it. But there is still blow up, there is still blow up in your barrier, but you are getting closer and closer to your boundary. All right? OK. Now, because of this blow up in the function, again, you expect ill conditioning, and you get it. I mean, that's, yeah. In fact, these methods, both the penalty and the barrier methods, go back to the 60s. The nonlinear optimization people have developed them in the 60s. So decrease mu, minimize your barrier, simple method. You have to stay strictly feasible at all your starting points for all the constraints. You can initialize from this and minimize your barrier for a new mu, drive mu to 0. You have to be careful with your line search and trust region because you have to maintain strict feasibility. So when you solve now for your line search and for your trust region, you will additionally require this condition on your line search or on your trust region. So, but you have, at the very start of your method, there's no question you have to be able to compute a strictly feasible point. Okay? This may not be a trivial calculation, but if you can do it, you can definitely apply these methods. OK. You can have convergence. So again, I can prove to you for these methods that the barrier stationary points correspond to approximate first condition in KKT. In particular, in that case, you have different things here, but you have that the minimizers are, the multipliers are positive because you're keeping Ci positive. The multipliers will be positive. The problem is that is exactly what I said, that you want to find the multipliers that are 0, the constraints that are 0. That will dictate what your solution is. And this is why you run this method for decreasing mu. And what you notice in the algorithm is that some of the multipliers will start approaching 0, and some of the constraints will start CI approaching 0. And you try to then guess which ones are active, which ones of them are truly 0 or not. Okay, yes, you get very bad ill conditioning. Your Hessian is like 1 over mu, mu goes to 0, blows up. Again, you need primal dual methods. And I want to pause for a moment and say, these methods were invented in the 60s. The ill conditioning of this method is so profound that the nonlinear community stopped using them. Okay, by the 70s, they were out of favor. There were no primal dual methods at that point. And then in 1984, Karmakar invented, and well, Hachiyan before him invented the ellipsoid method, and then Karmakar came up with his method that showed polynomial complexity for linear programming. And some people at Bell Labs showed that actually that method is nothing but a barrier method, but for linear programming. So there is this profound connection, and it's maybe to be understood because polynomial complexity means you get rid of the combinatorial aspect of your problem. And this is exactly what these methods do, because you stay feasible, avoid the boundaries. And this was a profound idea that made linear programming solvable in polynomial time. So I wanted to make that connection because it's very important. But the linear programming, but it was a non-standard idea because you use nonlinear methods, including the log there, right? Makes a linear program nonlinear. But it gains you something. But then linear programming people invented primal dual methods and all sorts of nice features, sorted out more issues on linear algebra. And so then these methods were revamped for nonlinear problems. And there are now very, very powerful solvers out there for nonlinear, non-convex problems that use interior point methods. Right, so that's a nice story. There are many other methods that I have not covered for constraint problems. I just wanted to give you an idea. You don't have to make it totally unconstrained from the start. You can do Newton kind of steps for the Lagrangian, and you get this kind of sequential quadratic programming methods. You can do projections on your constraints, and then you get these active set methods, but then you get the combinatorial aspect. However, I should say that if you have simple bound constraints for your problem, you can project your search direction. You don't necessarily need to go to the machinery of these penalties or interior points. Okay, then you have other things like filter and so on, and it gets more and more complicated. I'm going to pause now, and we'll start talking about derivative free in the last hour, last 50 minutes, last 45 minutes. Okay, so please, if you can come back here in a few minutes. Okay, so first of all, I just like, as a comment more than anything, how do you give derivatives to a solver? Right, so let's say you have a problem. You want to get an optimization code, and you want to solve it with that code. Okay. Let's say you want to use a derivative-based code, right? Then you would have some piece of code that, say, gives the function value to the solver. And then to give the derivatives, you could have another file that gives the gradient, that contains the gradient if you can calculate the gradient explicitly. If not, you can use these other tools. You could use symbolic differentiation. But one thing that is actually quite well developed now is so-called automatic differentiation. So you don't need to write your own code for this. I strongly recommend you don't. I mean, this automatic differentiation code, what it does is you give it your function code. So the code you have, the file you have that has function description of your function in it. Provided that function can be written as a combination of basic functions. So essentially, you have an expression for it, okay, for your function. Then these tools will differentiate your function. And it will create a file that has the gradients in it, or Hessians. And this is done by repeated application of chain rule and breaking down of your code into basic functions and operations. Okay, this is very good solvers. I mean, this is very clever techniques. If your function is smooth and you don't expect noise, a very easy thing to do is finite differencing. Again, there is good code out there. It's not so trivial to write a good finite differencing code. But for example, there are optimization interfaces like Ample that will already calculate the finite differences for you. So finite differencing is another approach. And I would say if you have a problem and you can compute at least gradients accurately, directly, or through one of these tools, including finite differencing, derivative-based methods would, in general, give you the best performance compared to the methods I will talk about next. But if, for some reason, you cannot do any of these tools, including finite differencing, if finite differencing, for example, is, say, too expensive for you, for your problem, then there are other alternatives. OK, so derivative-free optimization. This is a sub-area of optimization. And I just want to essentially first summarize for derivative-based methods that the one we've just seen, for say for unconstrained problems or constrained, they can solve large-scale problems. The linear algebra has been developed to be able to solve large-scale problems. But it requires accurate derivatives, at least through finite differencing. Derivative-free optimization is the sub-area of optimization that you should consider if you only have function values. You cannot calculate the gradients for various reasons. For example, your f is the result of a simulation, of an expensive simulation. You have noise in your function. You integrate some kind of, well, OK, I don't want to get into PDEs. You probably don't do PDEs here. So if you have noisy function values or you can't estimate the gradient by finite differencing, then you may want to consider derivative-free optimization. The other remit of these methods is when f of x is expensive. Okay, if calculating f of x as a result of, say, a lab experiment, right, or running a code that takes a long time, then again, derivative-based methods will be out of bounds. Okay. I wanted to tell you that finite differencing is a bad idea if you have noise in your f, but I hope I don't need to convince you of that. Okay. So an example for DFO is, for example, tuning your algorithm parameters. For example, so this some of you will encounter with say machine learning. You will have to do hyperparameter tuning. You have some key parameters in it, like the starting point or initial trust region radius, like we've seen, or initial step size, or things like that. Then you want to find the best values of those parameters on a certain test set, right? This would be very hard to do if you have to differentiate with respect to the parameters. Okay. So I strongly recommend something like these derivative-free optimization codes. Also, very often, you may not want very accurate solution. That's another issue here. That you want a good value, but you don't necessarily want it to 10 digits of accuracy. Okay. So then, again, these methods are very suitable. Right. So these methods, the idea of these methods is that they will not explicitly approximate your gradient. They will just not do that. And this is why they are suitable for noise. There are various methods in this. Direct search, model-based, pattern search, Nelder-Mead, random search, etc. There are stochastic and deterministic methods. I will talk about some methods that are very principled and connected to methods we've already talked about, called model-based. They are trying to be, these methods, essentially all of them, quite careful with, well, not all of them. They are trying, but not all of them succeeding, to be careful with your function evaluations. And the other thing to say is that you could apply these methods for non-smooth and even for global optimization. We've recently tested them as well as for global, and they actually work reasonably well. They work actually much better than Bayesian optimization. OK, what is the limitation? I should say this up front. There are some mechanisms in these algorithms that make it very expensive to apply to problems larger than on the order of 100 variables. Okay, if I should say, if you're for tuning your algorithm, you have more than 100 parameters in your algorithm. Okay, that's maybe a time to reconsider your algorithm parameters. But essentially, you cannot do large scale with this, not yet. For theory, the underlying function, we are still sort of in general assuming it's smooth. But also, you cannot get the same high accuracy in your solution as, say, with Newton. But I'm working now quite a bit in these derivative-free methods, and you can get reasonably higher accuracy for all practical purposes, really. I mean, it's OK. This is not a big restriction, big limitation. But it's getting more and more expensive to solve to the accuracy of Newton, and sometimes, and especially in noise, you will need a sufficiently large budget for it. OK, so this ties in very nicely with the trust region methods we've seen. Right, so first of all, I'm going to go back to the idea of I want to do models. I'm going to keep the same principles of my optimization. I'm going to approximate my non-convex black box, very black box F, by some model. But now I can't use Taylor models. So how can I construct a model of my function just from function values and without trying to mimic Taylor models? The answer is by using approximation theory techniques and interpolating F on a set of appropriately chosen points. That's it. So I'm going to choose a sample set. And this sample set is not going to be clustered, around one point tightly, like in finite differencing. So a sample set, still local, but well spread out. I have a base point xk. That's my current iterate. And it's in this set. And it's the best value of f I found so far. Then I'm still going to calculate a linear or quadratic model. OK? But these C, G, and H are now going to be obtained by interpolating f at my sample points. OK. So I'm going to ask you, how many points do I need to calculate to compute a linear model on y, on the sample set y? I need n plus 1, where n is my problem dimension. How many points do I need to construct a quadratic? I need order n squared. Because of the non-convex nature of the landscape, I will have to, if you just use linear models for general optimization, it will be quite inefficient. It will be essentially more like steepest descent, right? So you have to put in some curvature information. So if you go to order n squared, then imagine that to calculate my model from here, I have to find my H and my G and my C. This will give me a big linear system. Okay? So this step is not cheap. But I can construct my model. And then what will I do? I will do trust region. My interpolated model will, in general, be non-convex. Quadratic, but non-convex. Now I can't do BFGS per se and so on. No, I'm going to get my model. And whatever it is, it is. So then what we do is the trust region is a very, very natural framework here. Also, the trust region will play another role. We'll see in a moment. So we are going to construct a model by interpolation, solve a trust region subproblem, and then do usual steps like in derivative-based model. We're going to measure the progress with respect to the true function. If we don't make much progress, or any progress, we are going to shrink delta k. All right. Now, we have some issues here, though, that are not the same as before. We can have steps where the model is not so bad, but it's degenerate. So I have taken, let's say I've taken a step where I have not made much progress in f. In derivative-free methods, I will not know whether this lack of progress was because I've gone too far with my step, or because I don't have a good model from the point of view of geometry. So in derivative-free, you can have these two different kind of problems. The model is good, but I've gone too far. Shrink the trust region. The model is not good. I've not gone too far, but the model is not good. It's degenerate in some sense. Shrink the trust region. So I have this issue that I have to constantly monitor the geometry of my interpolation set. Okay? So this is because, first of all, the first thing I need, I'm going back in my slides, this is a linear system, I said, right? The matrix of this linear system has to be well defined and non-singular for me to be able to interpolate. All right? This is definitely something I have to secure in each iteration, but this is doable. But I will actually do more on each iteration. I will, especially if I can't make progress, I will actually make this point spread out, well spread out. Okay. So this geometry step here tries to achieve both that the interpolation system is well defined for computing my model, and that the points are spread out enough that the model is actually good, a good representation of my function. Okay. The other thing we do in these methods is that I said to you that I need a lot of function values to calculate my models. I need order n for a linear, order n squared for a quadratic. Okay? This is the cost of finite differencing, right? This is quite expensive. I said that I want these methods to be cheap in terms of function evaluations. I don't want them to require me to evaluate f, because f may be very expensive. So what these methods do is the following. They start, for example, at the origin and take another n points or 2n points along the coordinate directions. Distance 1, okay, very specific, nice simplex to start with. Okay. Then they construct a model of my function interpolating on those points. I take the first, I set up a trust region so that all my points are inside the trust region. And then I solve my trust region and so on. Now, when I solve my trust region, and I found a point, a good point or a bad point, I will say I found a good point and I move to a new point. I am not going to recompute all that order n set. I'm going to take my worst point set, say from my y, replace it by the new point that I found, the better point, okay? And that's it. So I'm going to actually just update my interpolation set, not recompute it from scratch, just update it. Yes?
When you say the worst point is in terms of function values?
Yeah, function values, for example. So function values, if it's a good point. If it's a poor point, if it's I have not made much progress, then the worst point could be the point that worsens my geometry. Yeah, good question. So the idea is that, yes, maybe the startup cost in the methods out there, not in all of them, but in most of them, is you pay a price for the startup cost. But then the next steps are very, you try to just have order 1 evaluations per iteration. And for the geometry, you do various things coming from approximation theory. You use Lagrange polynomials. You try to actually evaluate the following. You evaluate how much you're changing your points in the set shifting them around would change the volume of your set. And you choose to give up points and bring in new points that increase the volume of your sample set. And you can do this, actually, and you can do it quite carefully with order 1 evaluations. You could get in terrible situations, and then you may have to pay the price of order n per iteration sporadically, okay, when all else fails. But in principle, the cost will be order 1. Okay, so still, the reason these methods don't yet scale up very well is because of the interpolation, very much so. So if you want to bring in curvature, you have order n squared function evaluations, and then you end up with solving an order n squared system for the interpolation. And then people try to do something simpler, like a quasi-Newton-like idea. So, for example, you say that you're going to choose less points here in the interpolation, okay? And then the rest of the degrees of freedom in your age, you're going to compute it by minimizing the change from the current age in a Frobenius norm, and that actually is one way to view quasi-Newton ideas. So for example, you could say, I want to put here just 2 n plus 1 points. So n plus 1 point will give you a linear model. Another n points will give you like a diagonal quadratic. Okay. So you want to get that accurately from the interpolation, and then the rest of the points you will just get them from this additional optimization problem that you can solve. Yes.
This kind of local quadratic model fits my underlying function locally in some sense. How do you get that bit? So you're talking about how you fitted it, how you chose your interpolation points and your other values. What do you mean by like you maximize the volume in a sense to like optimize?
So the volume of those points, you can write it in terms of the determinant of the matrix, of your interpolation matrix. And then essentially it's complicated. There is a connection between that determinant and the size of your Lagrange polynomial. There is a property that tells you that these actually are connected, and so essentially by maximizing Lagrange polynomials, it turns out that you increase the volume. So essentially, you have to maximize Lagrange polynomials associated with your sample set, which sounds terrifying, but it's actually doable. So, yeah. Right. So we can do something a bit cheaper, but these order n squared models, they really work very well for noisy functions. But then there is a cost, and so the methods don't scale well. There is software out there, and for example, Bobiqua. We've used Bobiqua a lot. It's a very good piece of software. It's in Fortran. We are going to release a Python version very soon. And these are really actually powerful methods. And they work well on noise problems. And they are maybe not so well known. And they are, I would say, very recommendable for obtaining low accuracy solutions for global problems even. They are definitely competitive. Okay, we are almost out of time. So I've gone from derivatives, you have derivatives. Now you don't have derivatives. You may have noisy function values. So now I'm going to go to the case where you don't even have function values, essentially, or you don't have them accurately enough all the time. Okay, so we are now approaching more and more sort of the machine learning context. So assume that I'm in the model. For example, I could be in the model-based case. I've just told you in derivative free. I use stress region ideas. I use interpolation models. Now, these models, the way we constructed them just now, they will be accurate enough in general. At least you can fix the geometry to make them accurate when you need them. You can prove nice properties. You can prove global convergence. They're very nice. There is good code. Now assume that I have errors in these models because I compute the models not by interpolation, but by sampling. So I'm going to sample in some trust region delta k. All right. My trust region. I'm going to sample in it to compute my model. Or, for example, you can think of it as very inexact iterates calculation in my derivative-based methods. For example, you can even think here of batch methods and stochastic gradient. Okay, so I have I take a subset of my gradients in stochastic gradient. Okay, if you don't care about stochastic gradient, that's fine. Right. So what we assume here is that these local models of my function are sufficiently accurate only with a certain probability. All right. So let me say even a bit more. So okay, I told you random sampling of function values in a ball of delta k would fit this kind of models that are accurate with a certain probability. But assume, for example, another thing. I want to do derivatives. I'm going to do finite differencing in parallel. I can do finite differencing. And I have processor failure. Should I wait for my derivative from that failed processor to come back to me before I compute the gradient step? Or should I just keep going with however few finite differences I have? Okay. How tolerant of this kind of failures will my algorithm be? Okay, the answer is very tolerant. Consider trust region local models, okay, with this kind of approximate first and second derivatives. Then the question is how many iterations to generate, expected number of iterations to generate sufficiently small true gradients, okay? So this is one framework. It's quite a general framework because it includes a lot of different methods. So here, okay, I'm doing this very approximate and this very approximate, okay? And it can be sampling, it can be it's randomized, okay? So I have a local random method. For the time being, I still assume this is accurate, okay? But essentially my model is random. I still have a trust region. So now, of course, everything becomes random. My method is a randomized method. Okay. So then what I'm saying exactly, it gets a bit technical, but the idea is my model is accurate only with a certain probability, okay, per iteration. So I have some condition on this G. I write it here with big G because of the random variable. So is that, and it's close to the true gradient time with a multiple of delta where I'm doing the sampling, okay? Now this sampling, I'm saying per iteration is accurate only with a certain probability. So in some iterations, it could be terrible. It could be profoundly inaccurate. It could be biased, provided it's from time to time it holds, okay? Now, of course, in my algorithm, I don't know when it holds and when it doesn't hold. So what will I do in my method? What will I do in my trust region method? I'll do the same as always. I'm going to calculate my approximate decrease. I'm going to take the step if my f decreases. If not, I'm going to redraw the model, resolve it. There is one difference, though. I have to redraw the models when I don't make progress, okay? So usually, here we do redraw on unsuccessful steps as well. And when you, yeah, okay, right. So I said you could fit in here. This sampling. You can do second order. You can do batch-like methods. You can fit this kind of frameworks into this generic framework of probabilistic models. So the kind of things we can prove is that actually f is sufficiently small, same conditions as before. Gradient of f is Lipschitz. Then probabilistic trust region is globally convergent with probability 1, okay? Provided these models are sufficiently accurate with probability greater than 1/2. That's very weak. I mean, that's a lot of failures in your processors, okay? Hope you don't have such a bad cluster. Okay, so we can actually give a lot of guarantees for under very weak assumptions on your models. So these methods are actually incredibly robust. We have very general frameworks of it. We can do line search. We can do first, second order kind of ideas. And we are also then gone on to the next level up when I don't have accurate f either. So now f is truly stochastic in the function as well. Provided when I evaluate my f, I redraw, I re-evaluate, I draw an independent sample from the sample of the model, then we can have our framework. So in other words, in this kind of framework, we say, OK, the model is sufficiently accurate with a certain probability. The function values are sufficiently accurate with a certain probability. And what we can show is that if these probabilities are both large enough, so it's no longer just greater than a half for stochastic, if these probabilities are large enough, then again your method will behave, essentially like a deterministic method, worsened by a constant multiple, really. Right. So these kind of classical adaptive ideas are actually quite powerful. Right. I'm going to end now. So. I know that some of you are coming to optimization from application areas. And what I would like to encourage you to do is to explore some of the literature that the optimization community has been developing since the 60s, really. Some of these methods that I've talked about are maybe in themselves too expensive to apply to machine learning. But there have been further developments beyond what I've said here. I've really presented the basic kind of ideas that you can look at and that try to maintain sort of the principal aspects of earlier optimization developments. There is scope for more and new optimization, especially when it comes to big data and cheaper methods. I would say from what I've talked about, right? You needed approximate gradients, or some kind of function values for interpolation. When you go to machine learning, many people don't do a line search. Will you gain from a line search rather than using a fixed step? I believe you could if one tried it, maybe. Will you gain from going beyond first order? First order methods, or just gradient methods, are very, very badly affected by conditioning. There's no question. Machine learning has moved in the last 2 years more for second order methods as well. So yes, second order in itself is too expensive. Newton is too expensive for machine learning. But you need some curvature if you want to actually optimize over non-convex landscapes. What is appropriate curvature? These probabilistic models I presented are essentially like subsampling for the Hessian. You will find some of these ideas from what I've said in recent machine learning literature. And we do sometimes have to do something, like I said, cheaper than even a full gradient. Right. I have not said anything about discrete. I hope that next term the advanced optimization can be on discrete optimization. I'm trying to set that up with a colleague of mine. And I have not said very much about global optimization. But I do want to say that if you really, really, really want the global of your problem, the state of the art is pretty discouraging. You can solve problems on the order of 10 variables, all right? You can solve thousands for derivative-based. So there is a lot more work, but it's also NP hard. So in general, we probably shouldn't expect to be able to reach scalable methods for global. I would say that there is some glimmer of light in terms of special structure global, right? This is a very modern trend in optimization. You have some special structure where you can find the global. And that, for example, is what some people in machine learning are finding about certain problems connected to, say, matrix completion, connected to phase retrieval, and other instances. So there is now with machine learning moving so much towards deep neural networks, there is a renewed interest in non-convex optimization, and I think, you know, it's time for old and new ideas to sort of come together. Okay, thank you for your attention. I'm very happy to talk about questions. We have, I should say, an optimization club at the Turing, where people can bring their questions on optimization. Actually, one is tomorrow. But if you want to join, you should contact Adiletos Demisov. He's another PhD student here. And so we are trying to run this. You know, you're working on something, you have an optimization question, you don't know how to go about it. Please feel very free to bring it to this club. All right? We are focused on applications. Yeah. That's the point of it. It's not a reading group. It's actually you bring your research, bring your optimization questions, and so on. Okay, thank you for your attention.